Hi class. In this video I want to move into section 2.3, and this section is about graph sketching, so it's asymptotes and rational functions. So I'm going to break this lecture into two videos. The first one I'm going to do is I'm going to talk about what rational functions are and what the two types of asymptotes we could have are, the vertical and horizontal asymptotes. And then what I'm going to do is I'm going to do a lengthy example that talks about curve sketching. So it's going to go back and it's going to be kind of a review of sections 2.1 and 2.2, where we talked about critical values, increasing, decreasing, points of inflection, intervals of concavity, and so on. But we're going to add asymptotes to it. Okay, so I'll break that into this second lecture for this. Okay, so just to start, what again is a rational function? So a rational function is a function f that can be described by this. So f of x is equal to p of x divided by q of x. And here p of x and q of x are both polynomial functions. Okay. Obviously here the domain of s consists of all inputs x for which the denominator does not equal 0. Obviously, the value, what's not in the domain of the function f of x is any value of x that would cause a divide by 0. So just recall q of x cannot equal 0. Okay, you cannot. So what's going to happen when you have a rational function and you were to, what would the graph look like if around values of x that would cause a divide by 0? And that leads us into what is a vertical asymptote. So a line x is equal to a is a vertical asymptote if any of these limit statements are true. Okay, so if you have your function, okay, and you look at the limit, so you have the one-sided limits. So let me just draw a sketch here so you can see what's kind of going on here. Okay, here's the value x is equal to a. And what we're saying here is x is equal to a is a vertical asymptote. So if you go to a from below, so from the left, and your function increases without bound, goes to infinity, or as you go limit as x goes to a from below decreases without bound, like this, or the flip side as you go from the right here, increases without bounds, or decreases without bounds. So the limit as you look, as x goes to this a, it increases or decreases without bound. You have a vertical asymptote. And that's what we're saying with the calculus here. But if you look here for a polynomial function, really what's going on here is the graph of a rational function never crosses a vertical asymptote, as you're seeing here with these lines. It's going to butt up against it. Okay. So if the expression that defines the rational function f is simplified, meaning that it has no common factors other than -1 or 1, then if a is an input that makes the denominator equal to 0, okay, the line x is equal to a is a vertical asymptote. So what's going on here? For f of x is equal to this p of x over q of x. Any values of x that cause q of x to equal 0, so any value that you would plug into the denominator and have it be equal to 0, will be a vertical asymptote. We'll talk later on about, there's some cases where if you were to plug in x is equal to 0 and have p of x be equal to 0 at the same time, then something a little different happens. So I'm just going to note all right, so when you plug this value of x in here, it has to be the denominator equal to 0, but the numerator will not equal to 0. All right, if you remember from a previous lecture, right, if you plug in 0 and you get 0 divided by 0, it's an indeterminate form, and it means you can evaluate the limit. So for this case here, okay, any value that would cause the denominator to be 0 but the numerator not to be 0 is a vertical asymptote. All right, so let's just do two examples here. Okay, determine the vertical asymptotes of the functions given by the following. All right, so look here. Here's your first function. You have f of x is equal to x times x minus 2 over x minus 1, x plus 1. And what the first one says here is, look, is simplified, okay? So let's simplify this first function here. If you notice, you can cancel the common factor of x here. And so now you're simplifying, it's just looking as x minus 2 over x minus 1, x plus 1. Okay, so even though you cannot plug 0 into this function, like if you plug 0 into this function, you get 0 divided by 0. That's that indeterminate form, not simplified. If you want to find the vertical asymptotes, you would just look here. So we have vertical asymptotes where this expression, x minus 1 times x plus 1 is equal to 0. And so we can see here, right, that you have two, this will happen when either x is equal to 1 or negative 1. So again, we have vertical asymptotes at you have one at x is equal to negative 1, and you have one at x is equal to 1. All right, now look at this function. This function is already simplified, okay? So then you're just going to look at the denominator, and we're going to have vertical asymptotes where this entire denominator is equal to 0. So you can factor this x squared minus 16, right? It factors into x minus 4, x plus 4, because it's the difference of two squares. And you can see in this case here, we have vertical asymptotes at, if you look here, first when x is equal to 0, when x is equal to 4, and then finally when x is equal to minus 4. So just make sure if you're going to look for vertical asymptotes, you simplify if possible. Okay, so it needs to be simplified. All right, now let's talk about horizontal asymptotes. So the line y is equal to b is a horizontal asymptote if either of the following statements are true. If you look at the limit as x decreases without bound of the function, the limit exists, or as the limit as x increases without bound goes to infinity of the function, it exists. So a horizontal asymptote for some graph is going to be a horizontal line like this. And the graph, as you increase without bound, it's either going to come down like this or butt up like this. And then as you decrease without bound, it's going to go like this, or it can go like this. Okay. So just basically the limit as x goes to negative infinity or positive infinity, it exists and you can evaluate it. I'm going to show you first how to solve this with the limits here, and then I'm going to show you just like a trick with it. Okay. And the trick first we'll do here is the graph of a rational function, and then I'm going to do two examples. I'll show you with the limit, and then I'll show you with the trick. So the graph of a rational function may or may not cross a horizontal asymptote. Okay, so what I mean by that is you can have the graph look like this. It can cross it, but eventually it's going to butt up against it. Okay. Horizontal asymptotes occur when the degree of the numerator is less than or equal to the degree of the denominator. Okay, so just remember the degree of a polynomial in one variable is the highest power of that variable. So if you look here, what I mean by that, so the degrees are equal, the degree of the numerator is less than or equal to the degree of the denominator. So for example, something like this. Say 3x to the fourth power plus 7 over 4x to the fifth power plus 8. Okay, notice the degree of the numerator is 4, degree of the denominator is 5, so it's less than, so we'll have a horizontal asymptote. In this case, when the degree of the numerator is less than the degree of the denominator, the horizontal asymptote will just be the line y is equal to 0. So it'll be the x-axis, okay, when the degree is less than. Now, if the degree of the numerators is the same, right, okay, so if let's just say it is 2x to the squared plus 3 over 3x squared minus x minus 1. Okay, notice how they're the same. So they're equal. This will have a horizontal asymptote. And what you're going to see here is the horizontal asymptote is going to be the ratio of the leading coefficients. So in this case, it's y is equal to 2/3. So whatever the leading coefficients are. Now, if it's different here, f of x is equal to, say it's something like 5x cubed plus 12 divided by x minus 1. Notice how the degree of the numerator is greater than the degree of the denominator. Okay, this will not have a horizontal asymptote. Now, there is a special case where if actually this had been squared here, so the degree of the numerator is exactly 1 more than the degree of the denominator, you get what's called a slant asymptote. And I'm not going to cover that in this lecture here. Okay. The ones we're going to focus on is this one, or it does not have a horizontal asymptote. All right, let's just do some examples so you can see. All right. I'm going to show you how to do with the limits here. Okay, for this first one. So determine the horizontal asymptote of the function given by. So what you're going to do here, you notice how the degree of the numerators are the same, right? They're both squared. Okay, so it's going to be the ratio of the leading coefficients, right? So it's going to be 3/2. But let's just work the limit and verify this. So let's look at the limit as x goes to infinity. So what you're going to have to do here is you're going to take everything and divide it by x to the highest degree. Okay, so this is 3x squared divided by x squared plus 2x over x squared minus 4 over x squared. Literally everything. Now let's clean this up, right? These x squareds will cancel. So you get the limit as x goes to infinity of 3 plus, this ends up just being 2 over x minus 4 over x squared divided by, these x squareds cancel, so you get 2 minus 1 over x plus 1 over x squared. Well, look, we know that as x goes to infinity, right, this goes to 0, this goes to 0, 0 goes to 0. So it's just 3 plus 0 minus 0 over 2 minus 0 plus 0, which is 3/2. Right, which is just the ratio of the leading coefficients. You got it. All right, let's do this one algebraically. So to do this, what you're going to do is you're going to FOIL it out, right? So you're going to get 2x squared plus 2x minus x minus 1 all over, FOIL this bottom out, 15x squared plus 18x plus 10x plus 12. Well, look, you can even clean this up. 2x squared plus x minus 1 all over 15x squared plus 28x plus 12. So look, this one over here, to go back, and I should have written this more fully. We have a horizontal asymptote at y is equal to 3/2. And over here, look, you can just say, okay, the degrees are the same, so we're going to have a horizontal asymptote at the ratio of the leading coefficients, which is y is equal to 2 over 15 here. So algebraically, that's just pretty straightforward and easy. All right, let's just do 2 more quick examples. Just so you can see here. All right, determine the horizontal asymptote of the function. So here, notice this one. The degree of this numerator is 5. The degree down here is squared. The degree of the numerator is higher. So this one here actually has no horizontal asymptote. Okay, now notice here, remember what I said. So the degree of the numerator is 2, the degree of the denominator is 3. When the degree of the denominator is larger, which it is, this has a horizontal asymptote at y is equal to 0. So if the degree of the denominator is larger, it's just y is equal to 0 as a horizontal asymptote. It's the x-axis. All right, what I'm going to finish this up with in another lecture video here, I'm going to talk about strategies for sketching graphs.